So, welcome after lunch. I hope you had a great lunch. I definitely had a bit earlier than maybe some of you, but good time to be back here in Oslo, beautiful city. I work for a company called Particular Software. We are the makers of nService Bus, and if you are interested, you can follow me on Twitter at Daniel Marbach. The good thing about people from Norway, they usually are the ones that can pronounce my name. When I say my name to Americans, it's like Marbach, and it's like, but Norwegians can actually say Marbach because you have the same hard vowels. That's pretty cool. Before I joined Particular, I was working for a company in Switzerland where we built this medical patient type of record system where we managed probably 4 million patient records of 4 million patients in Switzerland, and it was a huge legacy system that was running on 13 servers, million lines of code, and it was, let's say, a big monolith, although it was spread over multiple servers. And we had quite a few problems, and one day the customer came and said, you know what, we're doing medical type of invoicing, medical patient management. Wouldn't it be nice if we could also do general purpose invoicing? And then we said like, yeah, I'm not sure about that because we know that we have to change the system. And the customer was, yeah, I don't have a lot of money, but I'm sure you can make it, right? Have you ever had that in your projects? Yeah, exactly. Huh? And we were like, let's give it a try. We said, but let's start with an easy use case. So what we did is it's a simplified version. So we had basically a demilitarized zone, and in that demilitarized zone we had a front end service which was running on .cf service. And that did, for example, invoice refunds and queries against the backend server, and the backend server was doing some kind of remoting, marshalling of the data, and was doing all kinds of processing against with ADO.NET. We still used ADO.NET 1.1, although we were already running on .NET Framework 4 at the time when I left the project, was doing reads and writes against the SQL Server cluster. The SQL Server was fine, it was heavily optimized. We had a DBA in the project, so that was good, but the rest of the code was pretty complex. And one thing that we didn't really realize at that time was once we started moving towards general purpose invoicing, invoice refunds, we exposed ourselves to a whole new world. And that whole new world was, well, we had web shops that wanted to issue invoice refunds of their customers against our database, and they were using these invoice refund services. And one of the things that we realized was, well, okay, web shops, it means you are now, for example, even now during these talks, if you find something boring, you can open up your cell phone, go to a web shop and order a new and shiny cell phone, right? So you can do that 24 hours every day, 365 days. So we had to cope with much more load on the system. And that much more load could also quite increase because we had now suddenly all these interesting PHP, WooCommerce, whatever you want to call those clients that were connecting to our service. And one thing that we realized was that it seems to be quite common, especially in the PHP world, no offense to PHP developers, but at that time it seems to be really common that people started, once they issued a refund against our services, they started polling our query APIs all the time in order to see whether it's processed. I don't know what the impression was, that if they pull more, we process faster because they're so annoying. I don't know what it was, but so one thing that we basically lost the maintenance window in that architecture, right? Because when we shut down the backend or when we shut down the database, well, they cannot do invoice refunds anymore. They cannot do polling queries against our databases. So that was a big problem. So basically what we can say is we had this, what I call the RPC call stack of doom. And I don't want to say RPC is bad. Please don't get the wrong message. RPC, remote procedure style communication, whether you're doing it over .cf, old school way, or HTTP, doesn't really matter, is a good communication mean for some types of things, but not for everything, right? But here what we had is, well, whenever we had, for example, latency on the database server, or the backend was slow because we had garbage collection problems again, for example, because we had a lot of legacy stuff. Usually the latency rippled through the call stack to the front end calling web services. So that was a problem. Then when, for example, database transaction had to roll back because we opened too many connections against the database, that usually led to an exception. That exception then bubbled up the call stack to the WCF services. Obviously, we had good team members, and those team members actually found out that WCF is quite extensible. So we had some kind of behaviors in WCF that fished out those exceptions and made sure that it doesn't bubble up to the web service call itself. But still, when we had those kind of exceptions, we couldn't really handle any requests anymore. So we had a problem. We couldn't really fulfill the SLAs, the service level agreements that we had with those web shops, because we had a high temporal but also spatial coupling in that architecture. And the storage layer, or the latency of the storage layer, and the latency of the backend processing services directly affected the user-facing latency. And we could also not throttle things. For example, when we wanted to implement a maintenance window, or we said in that period of time, because we're rolling out some DB scripts, we only want to handle 100 invoice refunds per minute or per second, whatever that number is, we couldn't really do that. But then we realized, well, invoice refund is actually quite an interesting thing, because any invoice refund, especially the command side of things, we can pack it into a message or a command, and then we can just ship it to the backend and basically say to the customer, thank you very much, we got your invoice refund, and we will process it eventually. So we started saying, well, messaging is actually quite a good thing that we could apply to. So we went back to the drawing board, and we started basically drawing a new kind of architecture. Well, new kind of architecture is a lie, because, I mean, you know it, if you have a legacy system that is that huge, if you're coming to your teammates and say, we're going to re-architect everything, we do microservice the shit out of this system, everyone is like, are you crazy? Are you nuts? This is going to take multiple months and we will never achieve this successfully. So we said, let's do simple, small steps, start at the edges, introduce where it makes sense, a little bit of messaging, but never go all in. So what we did is, we slightly changed those WCF services. So what we did is we packaged the invoice refund command here into a message queue. At that time, we were using Windows heavily. We used MSM queue, but it doesn't really matter what kind of technology you use. We could also have done messaging on top of SQL Server, but since we already had some messaging code in there with MSM queue, we used MSM queue. And then what we did is we had a little front-end cache for the queries. So basically, whenever a command came in, we just updated the state, the invoice refund state in that local demilitarized zone in that front-end cache, and then the PHP client could hammer the shit out of us. That was not a big deal, because we were always serving from the query cache the queries. And then on the backend, whenever it had time, it could basically process the invoice refunds from the queuing system down there, and then do its thing. And whenever it's done, it could publish an invoice refunded event into the system that was subscribed by the demilitarized zone, invalidated that cache, and then the PHP client could automatically be notified, so to speak, when they pulled the invoice refunds. So what this gave us was pretty cool. So now we had a decoupling of the architecture. So the front-end services were no longer coupled directly to the back-end services. We could shut down the database, deploy some scripts, but we could still handle invoice refund stuff without any problems. We had awesome scaling vectors in this architecture, because we could say, well, whenever we are ready on the back-end side of things, when we isolated the invoice refund processing engine out of the big monolith, we can basically have copies of that component running on our servers, doing competing consumer on the invoice refund command queue, for example. We could do throttling, right? Because we can do throttling on top of queues, but we also got what was the biggest benefit for us, retries, because whenever we had a DB transaction timeout, transaction lock, or something like that, what we could do is we could just roll back the message into the queue here, and then retry at a later point in time. So that was pretty nice. And what we also found out is that because we are packaging the intent of the customer, the invoice refund command, into that message, serialize it to a storage-backed queue, we will never lose that intent, but we also capture that intent, right? So if you have just a regular HTTP call or WCF call like we had before, whenever there is an exception, the invoice refund command is basically lost. But with a storage-backed queue like MSM queue, we didn't have that problem. And one thing that I want to note about this pattern, if you're saying, well, that sounds nice, I maybe can apply this as well, you have to be a bit careful, because essentially what we did here, and we didn't know that at that time, but I learned something in the years I've done software engineering, or at least I hope. But what we essentially did, we did cache invalidation here, right, based on a business event. And if you apply this pattern too much and you fall in love too much with it, you're basically building a distributed cache on top of messaging, which is always a bit dangerous. So, but we felt, well, once we realized the problem, we felt in this specific kind of thing, it's actually quite okay. But I just wanted to mention that. So once we started rolling out those stuff, or started thinking and designing more and more, we kind of fell in love with messaging, at least for this part of the system. For some other parts, we didn't, because we said, well, WCF services querying directly against the database is still fine. But then we had a hard decision to make, because we thought about, well, we need some kind of a messaging middleware that allows our developers to focus on writing business code and not plumbing code and low-level messaging everywhere in the code. So we said, well, we can either buy something, for example, or build something. And in that project that I was, we decided in that medical invoice system, we decided to buy a messaging middleware out of the shelf. In another project that I was, once I moved away from this project, we actually decided to build a messaging library, messaging middleware ourselves. And I want to talk today in this talk a little bit about the challenges that we faced. So if you're ever faced to build something like that yourself, that you have all the tools necessary to actually build a robust and reliable queuing abstraction yourself. Okay, so, but before we do this, I want to talk about the basic bits and pieces that we need for a robust messaging middleware. So, well, first of all, going back to the architecture drawing board here, is the front-end services. They need to be able to capture the intent, the messages, serialize it somehow, and send it over to the input queue. So that's the sending part, right? That's what we need. And then on the receiver side, we actually, in the backend, we need a receiver. And the responsibility of the receiver is basically consume the messages that are in the queue, manage the queuing connection, dispatch the business logic that we have based on message payloads that are coming in, and eventually, in this example, publishing messages back to the message cluster, to the messaging middleware. So really super simple. So let's look at some code. So what I'm going to do is I'm going to switch now to Visual Studio Code and show you the code that we started with when we started building that messaging abstraction library. Unfortunately, I'm probably going to block a little bit the view because I have to stand here in front of my computer. I hope you can still see the things. I will switch over the screen right now. So this is the first simple code that we came up with. So we have a message pump, and that message pump gets started. We have a cancellation token source because the cancellation token source allows us to properly, with a cooperative cancellation in .NET, make sure that whenever we want to shut down our system, we then properly shut down the system and we do not continue to process the things all the time. Then we have the pump task. So here I'm using a while loop that observes the cancellation token, and then what I'm doing here is I'm reading stuff from the queue. So for example, here I'm getting back a memory of byte for the payload and the memory of byte for the headers. I pass in the cancellation token to the underlying SDK that I'm using. Then what I'm doing is I take the raw byte information, the headers and the payload, and I turn this into logical messages. Logical message is the thing that your code is going to handle. Right, so what I do is I invoke some kind of a deserialization process. For example, I could be using JSON.NET, protocol buffer, whatever fancy tool you want to use there. And then what I do is I invoke this handle message code. And this handle message is in this quick demo. I'm just doing a task delay, and then I'm printing out something on the console, which I will show later in the demo. Then we also need, for that basic code, we basically need something to stop it, right? So whenever someone calls stop, what we do is we cancel the cancellation token source, then we await the task that is pumping messages, and then we dispose all the resources that are disposable and shut down the system. So one thing that you might note here is I'm not using task.run to invoke this code here. I'm doing that because this code here is a pure async function, a pure IO-bound function. And if you're doing pure IO-bound kind of async await, you essentially never really need task.run, because task.run is for compute-bound stuff that you want to offload explicitly to the worker thread pool. In just a little side note about TPL and async await, right? So what I'm doing is I'm just casting this one to func of task, and then get it back, and this will start spinning. So this is the basic code that we essentially ended up building in our infrastructure. So let me quickly change the screen again. Back to the slides. If it's working. Okay, good. Good. Well, I showed you here a polling implementation of a message pump, right? So maybe you're using right now an SDK that has some kind of a more reactive way of pushing messages towards you. For example, you could be using a reactive extension or whatever. I think that doesn't really matter, right? Whether a library is pushing information to you or whether you're doing some kind of a polling implementation, it's not really part of this talk, because most libraries that push message to you, they also do some kind of a long polling underneath. So you just happen to be lucky that someone probably in that SDK already wrote the code for you, and that you don't have to worry about that part. But if you only have a polling implementation of an SDK that doesn't allow you to push messages, then you're actually ending up building that kind of code. Now let's look at the sending part. Well, I didn't really show the sending part. I only showed the receiving part of the message pump. I believe it wasn't really worth showing, because eventually what we do is when we're sending, we're taking the payload, the logical message that we got. Maybe that's an instance of a class with some data on it. We serialize it with our favorite serializer of the day, and then we send it to the queuing system. Because it's IO bound, it's going to be an await call as well. And we send in the payload and the headers that represent additional metadata that we want to send to the receiver of the message. So let me do a quick recap of what we just saw in this code demo. So basically, with a little bit of TPL hand waving and a little bit of async await sprinkle magic over the code, we got a message pump that is working fine. We have cancellation support, so we can shut it down. And this worked really well when we shipped this to production, until a specific moment in time. And well, what we got is rush hour. And well, once we had a web shop that has some precious items on the web shop, and those web shops were sending in hundreds and requests. Then basically we have a rush hour problem with this code. And why do we have a rush hour problem? Well, the thing is the following. If we look at this code, what the pump essentially does is, when there are, let's say, 3 messages in the queue, we take the first message out of the queue, invoke our code, right? And then we take the next message out of the queue and invoke our code. If the handler of that code takes 20 seconds, it takes at least 20 seconds until the next message is taken out of the code. So what we can say here is there is a metric called critical time in queuing system. And what we can say here, with the code that we wrote, the critical time that we had in our system on that specific queue went through the rooftop. What is the critical time? So the critical time is consistent out of 3 data points. So the first is the network send time. So that's the time that we spend on the networking layer with serialization and everything until the message is in the destination queue. That's the first piece of the puzzle. Then what we have is we have the queue wait time. And the queue wait time in this example is when we have 3 messages. For the last message, if handling a message takes 20 seconds, right, it's 20 seconds per message. So it takes at least 40 seconds until the 3rd message comes. So that's the queue wait time. And then we also have the actual processing time, which is the overhead of the message pump infrastructure, the overhead of deserialization from the networking layer, and then actually invoking our handler code. So that is the critical time that we had a problem with. And we said, well, that's easy, right? We are programmers. We can solve that. So let's roll back our sleeves and get some coding done. And then someone said, yeah, but now we need to introduce concurrency. And as we know, concurrency is hard. It's super hard, and not everybody understands it. But we said, we can do it, and let's give it a try. And before I go into the concurrency codes, I will quickly switch the screen in a second. I just need to, okay. I will quickly run the first demo so that you can see that problem. For some reason, it cuts off a little bit of the screen. And let me zoom in a little bit. Is it better visible now? Okay, so that you believe me that we had a problem. I'm going to run the first version of the pump. Like you can see here, is we're handling the first message, the second message, the third message, the fourth message, and the fifth message. So let's have a look at the code changes that we did. So this is the concurrency pump that we wrote. So as you can see here, the code is pretty similar. So what we do is we have a while loop, which also observes the cancellation token. And then what we do is we have this fetch and handle message action that is the code that we had before. So we read from the queue, we deserialize, and then we invoke the handle message. We have the same code here. Task delay of 1,000, then pumping, we print out something to the console. And then when we stop, we cancel the cancellation token source here. I'm canceling it in 100 milliseconds. You will see later in the demo why. And that's basically it. So fire and forget, just for your curiosity, this is just a method that is empty that accepts a task. Why do I do that? Well, if you have async await-enabled code, and if you're not awaiting a task that is returned by a method, usually the compiler tells you you're probably doing something wrong, right? So what I need to do, I need to consume that task, and I need to tell the compiler, dude, I know what I'm doing, so please shut up, okay? You could also, instead of having a method that accepts a task, you could, for example, do underscore equals, and then basically we call it dropping the task on the floor, because we're not really interested in the outcome of the task. So let me go back to the slides and do a brief recap. So what we did is, instead of sequentializing the call like we had before, right? Every await statement in the code is sequentialized here, and when the IO-bound code is done, wake me up again so that I can process the next thing. So instead of sequentializing, we said, okay, let's just do a fire and forget. And we said, well, this is pretty easy code, right? There's nothing really worrisome about it. Do we need to really test this a lot? Nah, no, we can pair review it. Let's just ship it to production, right? And well, that tiny little change, although it looks so harmless, actually gave us quite a few problems, because it worked again until this freaking damn rush hour. So it's interesting because in the rush hours, we're actually, or let's say our customers of the systems, they're actually making money because we are selling stuff, or we're refunding invoices, or whatever we are doing when we are processing commands and messages. But now, and we actually want to make money with the business, right? But in this specific case, because we introduced that tiny little change, we're actually losing money right now. Why are we losing money? Well, let's have a quick look. So what we have is the pump that we just wrote. It basically runs on an unbounded concurrency mode. What does that mean? Well, if you just have one message in the queue, it's fine because it picks it up and handles it. But if you have 1,000, 100,000 messages in the queue, it's basically going to spawn 1,000 or 100,000 concurrent receive operations from the queue, and it's going to eat up those messages. And we all have it in our dreams that our systems that we write and deploy have limitless resources, right? But every system has somewhere a weak link in the chain. And in our case, it was the database. Sorry, I'm unfairly blaming the database right now, right? I mean, but in this case, every database has a DB connection pool. And yes, you can increase the DB connection pool size, but up to a certain extent, when you're managing connections, it's either the queuing system directly, or in our case, the database starts choking, and then we might depending how we wrote the code, we might eating up all our resources and actually crash the servers or crash the DB, or we go into transaction timeouts and all kinds of rollback problems and make it actually even worse when we're running that piece of the code. And one interesting thing is that, well, we introduced a storage-backed queue in our architecture. We could have done retries and queuing in memory with the previous architecture. But we said we're using a storage-backed queue because we can trust that the storage has probably almost infinite resources. We can store all the precious requests that we get from our customers on a disk-based system, and whenever we have time, we pick it up. But now, because we have an unbounded concurrency, we're actually losing that benefit of the queuing system because we fetch too much stuff at the same time and start overwhelming the resources that are actually limited. So, well, we then said, we're good programmers, right? So probably you already have heard of semaphores or semaphore slim. There is a way how we can limit concurrency and how we can tweak the weakest element in the chain. So what we did there is we said, well, the DB, let's assume the DB can handle 100 connections concurrently. So all we want to do is we want to fetch 100 messages concurrently from the queue and no more. Right? If there is just one in there, we just pick one. But if there is 101 in there, we just pick 100 because we know that's safe in our architecture. That might be different in your architecture, but we essentially wanted to prevent to DDoS ourselves with messaging. So I'm going to briefly show you the demo from the previous the unbounded concurrency stuff. Hopefully you can see it. No, I'll need to move it over a little bit. So now if I hit enter, I'm going to use the unbounded concurrency thing. Remember, I just run this code on my 8-core i7 machine, 100 milliseconds, and then I immediately stop it. But already here, I'm not sure what the actual number is, but I think I'm handling in that 100 milliseconds before I shut down, I'm handling over 30,000 concurrent operations. Okay, I'm cheating a bit because I'm not doing actual I/O. It's just to illustrate what could happen, right? Of course, with I/O and latency, it would be a bit slower, but depending on your network resources, it might also be tens of thousands of requests that we would be handling here. So let's see what we came up with. So what we did is we introduced the semaphore slim. So semaphore slim is the more efficient variant of the traditional semaphore. It's, I think, up to 5 times faster than the previous semaphore because it uses a combination of spinning and waiting. So it's much more efficient. It doesn't introduce kernel transitions and that stuff. So we use that, and this is basically like a toll lane on the highway, right? We're saying, well, up to the maximum concurrency here in my example, it's 3, but with a DB connection, for example, it could be 100. We're saying we never want to pass more than 3 cars through the toll lane, right? The toll lane only has 3 paths to go through. And what we do then is when we pump here with the pump, we say, please acquire the semaphore. As long as the semaphore still has places free, as long as the toll lane is free, this code doesn't asynchronously block, right? So what will happen is we fall through here, and then we do fetch and handle and release. So we still do fire and forget. right? Because we don't want to have an await statement on this line. If you introduce an await statement on this line, we would, again, sequentially process messages. We want to concurrently process things. So what we do is, in this fetch and handle release, is we again read stuff from the queue, we handle the actual business code, and then we release the semaphore. We need to release the semaphore in the finally block so that we have more slots available again in the semaphore, or basically free up the resources in the toll lane, right? But then we also realized is that, well, when we shut down the system, we might have messages that are still processing for a period of time. Right? For example, you're shutting down your server or your receiver component, because you can now with messaging, right? Because we have a storage back queue, but you don't want to basically abort in the middle of processing. One way of doing that when we have a semaphore is we can introduce sort of a graceful shutdown. So we can tell when we cancel the cancellation token, what you can say is this loop will no longer continue. But resources that already acquired the semaphore and got a slot, that are currently processing in this fetch and handle release, can still have time to basically do their processing and shut down. And by the way, that's up to you, right? You might have different requirements, but here I'm just showing that little trickery. What we can do is we can have a while loop that basically loops over the semaphore current count, not equals max concurrency, and then we do an await task delay, right? The asynchronous fancy version of thread sleep, but it doesn't block any resources. And then we pull essentially the semaphore until we know that all the slots are released. And then we know, because we canceled the loop, we're no longer receiving messages, so then we can gracefully shut down the system, dispose all the resources. That's another thing that we introduced in this limiting concurrency code. Good. So let's go back to the slides. So in recap, what we can say is, with the introduction of the semaphore, we basically had a way to control the floodgate of messages that came into the system. And well, the code was pretty straightforward. We could ship it to production, and this worked really nicely. So this worked for months in production. We didn't really have any sort of runtime behavioral type of issues with this pump. So this was pretty nice. But one problem that we had was, well, as time started passing, well, I was the technical lead in that project, and I was tasked to build this messaging abstraction. That was a lot of fun, right? There's nothing better than distracting yourself from these damn business requirements and writing some fancy infrastructure framework type of code. That's what at least I love it. I'm not going to assume that you love it too, but I love this really. And so I did that, and I had this Mercedes-Benz in mind. Well, we're here in Norway, right? The land with probably the most Teslas on the planet. So it's probably more a Tesla Model 3 that I wanted to build in that time. So I did it, but the thing was, like always, right? As a technical lead in a project, your time is precious, and everybody wants something from you. So at the beginning, you have a lot of time, you build it, and then you need to still deal with these damn business requirements, and you're moving away, you're not touching the code again. And then the team started to extend that messaging middleware that I built under pressure. I know what you're thinking. He's going to blame the team. Actually, I could. No, it wasn't their fault. I mean, it's of course, it's like every project has pressure. We need to deliver business value, and that's what we're here for, right? So, and then over time, when we started extending this, we had more and more requirements that we needed to build into this framework. So one of the things that came, well, for every message that we received successfully, we want to audit the message. That's one example, right? Or, oh, we need to think about transactions and all that kind of stuff. And then we started to make this code, I call it flextensible. So let me show you how this code might have looked like, and let me also show you the previous demo with the concurrency limit. So now, when I'm running this code, this is the pump with the limiting concurrency that we built before. So now, as we can see, we always have like we handle 3 messages concurrently, And once we have no more messages in the queue, we gracefully shut down, and we are done. But let's go back at what happened, and this is just an illustration, right? I hope you get how abstract I have to show this a little bit. But what we did here is, well, we said, okay, how about for the auditing part, we need some kind of extensible middleware that we can plug into, sort of like Owin, that we can plug into our messaging abstraction library. So the basic bits that we just build is still the same. Use the semaphore, we gracefully shut down, but now the complexity starts raising in this code. So what we realized is, well, we have to have some kind of a transaction that wraps the queue receive. When the queue is transactional, we have to have a transaction that makes sure that when we receive the message and we have an exception, that we successfully roll back the message again into the queue before we actually read the message transactionally. Then we also realized that we have some kind of infrastructure on our dependency injection container that we loved at that time, that we need to potentially resolve per message that we handle and pass it on to the object hierarchy that we're resolving when we handle the business requirement. So we built some kind of a child service provider abstraction. You probably have heard of ASP.NET Core with the service provider there. It's something similar, but we wrote it on our own, right? The wheel gets reinvented every time in software development. So we did that, and then we said, oh, okay, now we need we need some kind of a middleware so that we can plug in the stuff, and we came up with this func handler context, cancellation token, task, cancellation token array. Ooh, sorry, probably your head is now exploding, but and this is the extensible middleware that we came up with, and now we're no longer directly handling the business code, we're invoking the middleware. And as part of invoking the middleware, when that's done, then we complete the transaction. Of course, like every framework that we write, we had also some to-dos in there. What should we do with the exception handling? And then a middleware looked like this, right? This is basically a function that we can plug into the middleware that can wrap the execution like Owin or like ASP action filters and stuff that can wrap the execution of the pipeline. And somewhere deep down, we had the actual business code invocation where we used our child service provider abstraction factory to resolve the iHandle messages that we came up with and then invoke all the handlers. And once that's done, invoke the rest of the pipeline. And I'm showing here a for each with an await. You could also handle all those implementations concurrently by using task when all. Of course, that's an implementation detail. But that's more or less how the code started to look like that we built. So the funny part is that, while I wanted to build this Tesla Model 3, over time, because with pressure, we probably built more this rusty little car. And depending who you asked in the team, some people didn't like that code or said, oh, it's dangerous, I don't know, it's too complex, semaphore and crazy concurrency, I don't want to touch it. So for them, it probably looked like this. And for some other people, like me or some other fans that became fan of this code base, it looked more like this. Right? And by the way, happens when you prepare a talk and you're procrastinating and you search for funny cars and you find those pictures. And the interesting thing is, the guy's really enjoying himself here, but the coolest one is this guy over there. He looks like, what the hell is he doing? Anyway, but then what you can say is, what I just did here is I only talked about the basic bits, about the send and receives, but we also have to deal with transactions. I quickly had this in the code, sort of hand-waved a little bit and say, oh, we need to have some kind of a transaction. I think if you're writing robust messaging middleware, you have to think about transactions and what's going to happen. So let me illustrate that quickly. So code that is executed under handling a message is never side effect free, right? Because you're going to invoke business code, and as part of that business code, you're going to write stuff into the database, you're going to create transactions, unit of works, and all that kind of stuff. But you might also, once you start leveraging messaging more and more in that message-driven architecture, you might also think, well, I need to invoke Salesforce. Salesforce is sometimes down, so I want to be able to retry a Salesforce command or send something to Salesforce. Then you're going to use more messaging. So what you're going to do is you're going to invoke more messages or more send operations as part of your message pump. So let's do a quick example. So when we have a transactional queuing system, what we can say is we start a transaction, we pick up the message from the queue, and then we invoke the business code. And as part of this business code, we're, for example, sending a message to destination 1, to destination 2, and we write something into the storage layer, which, for example, can be SQL Server, whatever thing that you're using. And once that is successful, we commit the transaction to the queuing system, or we abort things. The good thing is when you have MSMQ, for example, and SQL Server on premises, you have this beast hidden somewhere, which is called the distributed transaction coordinator. And the distributed transaction coordinator allows you to have a two-phase commit protocol that basically wraps all the operations involved here in a transactional way. So what it means is the SQL Server inserts are in the same transactions as the queuing system. So what we have is we have either successfully processed all the things. So we have successfully invoked the code, we have prepared the transaction to the destination queues, and we have prepared the transaction into the storage layer, and then we successfully committed all those, or we rolled back and no side effects happened. That's pretty cool if you have MSMQ and SQL Server. I'm not an advocate of the distributed transaction coordinator. Please don't get me wrong. I'm just saying if you have it, you might have it. That's a way to have transactional consistency, or from a technical standpoint. But maybe if you have your code on premises and you have some throughput problems, you might think about how about we move to RabbitMQ, because we heard that RabbitMQ on top of Erlang is much, much faster. It can handle tens of thousands of messages per second. Well, then what's going to happen is you're not only throwing away the plumbing code that we just wrote against the SDK of, let's say, MSMQ or SQL Server with ADO.NET, you're going to rip out that code and replace it, for example, with the RabbitMQ pivotal client that has its own assumptions, but it also has implications on the transactionality, because RabbitMQ, for example, doesn't provide what is called cross-queue transactions. What you have with RabbitMQ, you only have receive-only transactions. Receive-only transactions means that when you get a message, you either ACK it or NACK it, right? When you ACK it, the message is successfully handled. When you NACK it, it rolls back into the queue and will be dispatched again to your code. But all the other things might be still visible. For example, the storage stuff. So what we can get here is we can get into things like partial updates. So partial updates illustrated here can be something like, for example, we have two pieces of code that we invoke concurrently as part of the message handling transaction. And then the piece here in green, it writes to the database, and the red piece here, it writes to the destination Q1, destination Q2, and into the database. And now when the message gets nacked, those things here, the destination 1 and destination 2 writes already happened, right? So that's one thing that can happen with RabbitMQ, for example. But then we also have partial sends. Partial sends means at any point in the code when we invoke the networking layer of the driver of RabbitMQ, there can be failures happening, right? So for example, what could happen is that if we write to destination 1, then we lose the connection to the RabbitMQ broker. And if we don't have retries built into the driver itself, then this destination write will fail. We might roll back the message and retry it. And then we send out destination 1 message again and destination 2 message, but we already got the partial send visible on downstreams, right, that are receiving messages from the destination Q1. So what that means, the implication of this is when you're moving, for example, to RabbitMQ, your business code needs to be idempotent from a business level perspective. Idempotency is just a fancy way of saying whether the code is invoked once or multiple times, the effect is the same, right? So that's basically idempotency. But what it also means for the queuing abstraction that we are writing is where we place the C# code in that abstraction library is extremely important, because if we have the code at the wrong point in our code base, we might end up with business inconsistencies that we have to
to deal with, or even message losses in some scenarios. But then, like we know that software projects, they evolve over time. You're not writing everything from scratch new. At some point in time, you might move from on-premises to the cloud. And I call it cloudy with a chance of failure, right? As soon as we start moving to the cloud from our on-premises data center, whether it's cost effectiveness or whatever you want to use, we also have different transactionality mechanisms. For example, with AWS SQS, if you're running in the AWS cloud, what we have is we have receive-only transactions that are implemented with, they call it is a message visibility timeout. So what it means is for your code, it has to deal with message visibility timeout extensions. Message visibility with AWS SQS means, and by the way, that also applies for Azure Storage Queues. For example, if you're using Azure Storage Queues in Azure, means that once we get the message visibility timeout starts counting. Let's say it's 30 seconds. Now, if the code executes under 30 seconds, we're fine. But if the code takes longer than 30 seconds, let's say, for example, 45 seconds, then the message will reappear in the input queue while we're still processing that message. And we will handle the same business message multiple times. So we need to make sure that our code, while we're processing, continuously extends the message visibility timeout on the server. Or sets a high enough timeout that is good enough for most of our business cases. If you're using Azure Service Bus, for example, most people don't know that there is a concept that we call sense with atomic receive. Azure Service Bus has the possibility to use, together with transaction scopes, a thing that they call send via. What it means is, with send via is when we get a transaction, we start a transaction scope, we take the message out of the queue, invoke the business code, and instead of sending to destination 1 and sending to destination 2, what we do is we send a message to the input queue and attach a send via header to it. And that send via header says, well, by the way, if I acknowledge this message, please send that message over to destination 1 and the other message to destination 2. And then it's a guaranteed broker-side operation that will handle the delivery of the message. And one good thing is that if we fail to handle that message, if we have to roll back the transaction, no side effects from a messaging perspective will occur. But if we are successful, then the guaranteed operation of the broker kicks in and delivers those messages to the destinations. So with this mode, we can essentially prevent ghost messages occurring on downstreams, which is pretty nice. Obviously, I didn't mention it yet, but as you all know, if we have a transactional write into the storage layer, it could still be possible that although the message didn't go out, we still have partial inserts, for example, visible in the database. So the database insertion code that we write in our business handlers needs to be idempotent, still needs to be idempotent. But when you're embracing the cloud more and more, then there is another concept that we have to take into account how we write our business or message abstraction library. And that is what I call penny pinching, right? Because in the cloud, we do penny pinching all the day because, I mean, probably we're running on the credit card of our boss, right? And we don't like when the boss at the end of the month comes to us and says, why did you spend 800,000 Norwegian kronen on Azure's subscription or whatever that is, right? We don't want to answer those questions. So we better want to make sure that we efficiently operate with the platform as a service offerings that we have in the cloud. So for example, with Azure Service Bus, we might have 13 million requests included, for example, in the standard tier. But once we reach a certain threshold, for example, we start paying for 87 million operations on the broker. We roughly pay $80 per month per 87 million operation. And 87 million sounds like an awful lot, right? Because it's a huge number. But when you do the math, what it boils down to roughly 120 requests per hour. And that's not that much, right? So as soon as you start crossing that threshold, you're getting charged more and more and more, and you better want to make sure that you handle this efficiently. And now with the new Azure Service Bus SDK, what they also introduced is, because they're now heavily using the MQP protocol and no longer the SMBP protocol, what they introduced is you're getting charged per MQP connections. So what you get is you get included 1,000 connections in the standard tier per month, and then as soon as you start crossing more than 1,000 connections, you have to pay $3 per connection that you invoke against the Azure Service Bus. So that also has to be taken into account. But one thing that also comes is things are getting worse, because with the cloud and with this penny pinching, what we actually can say is every request that we do against the broker counts, right? So we want to make sure that we do less requests or only the requests that are really necessary. But if we have a queuing abstraction library that doesn't think about, for example, the latency that every call can have, then every single call that the developers are writing to that broker starts counting in terms of latency and in terms of costs, right? So what we have to do is we have to come up with, for example, smart batching, right? So what we want to do is we want to shovel as many requests as we can into one single call to the cloud. And most of those cloud SDKs, they offer you some kind of batching capability. And I kind of hand waved and said, we need to batch as many requests as we can into one single call. But what does that mean? Because every platform as a service offering, whether it's Google one or AWS or in even Azure, has some kind of limitations so that they can guarantee their SLAs. What it means, for example, if you're running with Azure Service Bus on the standard tier, you can batch up to 256K of requests into one single call. So what it means is you have to start estimating the message size of your payload so that you can make sure that you have only 256K in a single request. Once you have more, you need to start basically dividing it into multiple calls again. And by the way, if you're doing batching, one of the good benefits of batching is also you avoid ghost messages, because instead of doing 10 network calls that can all fail, you do only one that contains, for example, 10 messages, right? So you also have a much more robust and reliable code that you can do. And for example, if you're using Azure Storage Queues, you can only batch 64 kilobyte into a single request. So depending on the middle layer that the messaging cluster technology that you're using, you have different things that you need to deal with. If you're using RabbitMQ, for example, on premises, RabbitMQ can handle payloads of various sizes. You're basically only limited by the memory that you have available on your broker cluster, but it's clear, right? The more garbage you allocate even on RabbitMQ, the larger that your messages get, the more your throughput is going down, right? So you have to take that into account as well. Good, but now we actually have really the basic bits, right? So we have sending, receiving, transactions, but what we also know is software grows over time, and our infrastructure demands on the libraries and frameworks that we build also grows over time. So what we can say is we're living on the edge of sanity. So because what else do we need to deal with? Well, for example, we want to do competing consumers and scale out. So we need to efficiently handle the connections in the competing consumer scenarios. Then what we want to do is state management on top of the queuing system, for example. We want to have runtime configurations, routing configuration, or we need to, depending on the technology we're using, for example, if you're using Azure Service Bus, Microsoft doesn't really tell you how you map topics and subscriptions to queues, right? You have to come up with a topology that you handle on the Azure Service Bus broker namespace that is suitable for your project. And that might vary from project to project, and you have to re-implement it that over time. But the most important factor here that I want to talk about is not the actual code, it's the human beings that actually have to deal with that code, right? Because if you're the lead developer that is building that messaging abstraction, probably one thing that you constantly neglect is documentation, right? So when a new team member comes into that team, you have to essentially have the necessary documentation to teach the team member how to deal with that library. And then when, for example, you leave the project because you probably want to move to the next shiny little thing in your company and move away, then you're still the responsible one that wrote that library. But then there is also the aspects of now we're having a distributed system, and we probably have a distributed systems mess sometimes in the transition to a more and more and better architecture, because that's how systems evolve. We have to somehow know what's going on, right? Because, for example, if in production something is failing, how do we troubleshoot that stuff? How do we monitor? How do we visualize the things that are going on in the system? And maybe you also have things like you put it in production, it's running smoothly, running fine, and then at some point in time, the CEO comes and says, hey, we just acquired this new customer, and the message load is roughly going to be 100 million messages a month. Can our system handle that? And how do you answer that question? I mean, that's something we have to deal with as well. And the distributed system itself, they're complex, and there's no denying that, so we need some kind of tooling that makes sure that everything is running properly. And there is lots of ways you can monitor distributed systems, and I'm going to quickly show you one way of doing that. So for example, I have here a distributed system running with multiple endpoints, and if we're, for example, using what we call service pulse, you can have a look at what's going on. So you can see here all the different endpoints, you can see the message load, you can see here the critical time of our queuing system. And if we if we make sure, for example, that we process messages slower, and then if we increase the traffic in our system, what we can see is if we, for example, drill down into the queuing system, we can see that the queue length increases. We can see that the throughput rate, we can see the processing time is something.
It's flickering.
It's flickering? Okay, thanks.
Just, keep on.
Yeah, okay. We can see the processing time, and we can see how the critical time is increasing over time because we have more load. So one thing that apparently we can also hook into this to get notified. So for example, one thing that we can do is, well, we can fix the box and make this thing processing faster to essentially increase the processing time so that we can see that the processing time goes down over time, and then that means the queue length is going to get better. Or if we discover this automatically, we can essentially scale out an additional sales endpoint or even multiple sales endpoint. I'm simulating this here. And once they start spinning up, we can see here that we have now 3 instances of that sales endpoint running, and we can see how the queue length over time basically starts getting better and better, and how the critical time starts decreasing over time. And what else we get is, for example, if we have failures happening on our system. Let's say we just rolled out something that has a bug. We can see how messages start piling up here with errors. We can drill into those errors, and once we fix the bug, we deploy a new version of the code. And then what we can do is we can, for example, say, let's retry one message, or let's retry the whole group. And then we never actually lost any requests in that system with a message-based architecture. So let me go back to the slides and do a quick wrap-up, if it allows me to do so. Is the flickering gone now? Okay, good. Okay. Well, I showed you how, for example, we do it with the particular tuning. Of course, you can also do App Insights, Grafana, Prometheus, whatever fancy tool that you're using in your system. That's all totally up to you. But as a quick wrap up, what I wanted to tell you, I showed you, we basically unpeeled the onion here and we started crying, right? I showed you how we start with the basic bits, with sending and receiving, go into transactions and write more and more and more code, but it never stops there, right? And the thing is, as developers, as lead architects, as lead developers, our task is to deliver business value and not to write infrastructure. While you can now with this talk and you have all the things that you have to think about, the question is really whether you want to do that, right? So the make or buy decision is an important decision that you have to face in your projects. And I usually compare it's like doing surgery on yourself, right? It's like, well, you can do surgery on yourself. You can take a knife and cut out something that you have on your leg, but you're probably not a professional surgeon. That's my assumption. So whenever you have something that you need to operate, you're probably not doing that yourself. You trust a bunch of professionals to actually do that for you instead of cutting yourself and eventually bleeding out in the process of doing so. yeah, that was it. I hope you liked it. Thank you very much for coming. Thank you very much for staying here. And if you're interested and want to hear more about nService Bus that I showed here, you can go to go.particular.net/NDC Oslo 19-parsec. It's a gamified tutorial that allows you to play around with nService Bus. It's a planetary exploration game that you can play on yourself. It takes about roughly 30 minutes, and you go all into the bells and whistles of nService Bus. And if you're curious about the demo that I showed you, you can go to go.particular.net/demo and try it out yourself. And we also have tutorials how to do it with Prometheus, Grafana, App Insights, New Relic, whatever you're using to visualize the same metrics. If the code that I showed was too fancy for you and you would like to basically debug the code through and better understand it, I have all the code available on github.com/DanielMarbach/message pump. And if you have any questions, I have business cards here that you can take away, send me an email, or come to me. I'm still here at the booth, at the particular booth. If you have any questions, I'm gladly asking those questions. Thank you very much.